Welcome back. Right now, we're going to talk about what happens to the aromaticity count or the specifics of whether a molecule is aromatic or not when heteroatoms are present in the ring systems. So I'm going to start by kind of giving you a very rudimentary table to kind of base your classification and your analysis on. All right, so we're going to start with carbon, right? So if carbon has no charge on it, uh, and basically you don't have a double bond, right? So you have an sp3 hybridized carbon, and that will automatically break the conjugation, right? So just be on the lookout for that. But the idea is that that carbon is, just by itself, it's just a corner or the end of a line, but that specific carbon is not part of a double bond, so it is sp3. Now, on the other hand, if that carbon that's by itself, not part of a double bond, happens to have a positive charge, then under that situation, that specific carbon will be considered sp2 because, technically speaking, as a carbocation, it will have an empty p orbital, and the p orbital can totally overlap with the rest of the p orbitals in the conjugated system. So that is actually something to be on the lookout for. This one may be a little bit tricky because, technically speaking, when the carbon has a lone pair, that's when it develops a negative charge. That's a carboanion. And technically speaking, it is an sp3 hybridized orbital. However, it does behave somewhat like a p orbital simply because of technically it's kind of like a lone pair of electrons that is next to a p orbital. And roughly speaking, that hybrid orbital can overlap with the p orbital just fine. So, you could think of it sort of like an sp2 hybridized situation where the p orbital happens to have two electrons. Okay, so but those two electrons will be counted, as you go through the biggest loop in the molecule. All right, now with nitrogen, if you have a nitrogen with no charge, that technically will be sp3 hybridized, but it does have a lone pair of electrons. And much like the carbanion situation, you will count those two electrons as part of the 2 pi system or the pi system altogether. If nitrogen has a positive charge, that means that it's basically surrounded by 4 bonds. It doesn't have any lone pairs. So that will totally be a breaking conjugation, right? So in essence, that's the same thing as having a neutral carbon with no charge. If the nitrogen has a negative charge, then that means that you have 2 lone pairs on nitrogen. It will still be sp3 hybridized, but only one out of the 2 lone pairs will contribute to the pi system count. So 2 pi electrons are counted in that situation. And then one thing to kind of be also very keen about is that so far everything here, nitrogen has been sp3 hybridized, but you could also have a nitrogen that is sp2 hybridized, meaning that the nitrogen is part of a double bond. And in that case, you still have a lone pair on nitrogen, but the lone pair, due to the fact that it's part of an sp2 hybridized carbon, is trigonal planar, and it will be completely orthogonal to where the p orbitals are located in the system. So no pi electrons are to be counted there, even though a lone pair is present on nitrogen. All right, now oxygen, if it has no charge, it's got 2 lone pairs, it's still sp3 hybridized, but much like the nitrogen with a minus charge, you will only count one of the lone pairs for the actual pi system. And in case you're wondering, why all these rules are the way they are, it ultimately has to do with the symmetry of the orbitals. Only one out of the 2 lone pairs is going to have its orbital parallel to the other p orbitals. The second set of electrons will have no choice but to be semi-orthogonal to them, just because of the tetrahedral or pseudo-tetrahedral arrangement, right? All right, so let's see how it works out with an actual example. So here we have a molecule that does have nitrogen and oxygen within the ring system. And as far as looking at all of this, we have to realize whether or not we're breaking the conjugation, right? And for carbon, if you have a carbon by itself, it's not part of a double bond, and it has no charge, that's a breaking conjugation. If nitrogen is got four bonds and no charge, well, excuse me, it's got four bonds and a plus charge, that's a breaking conjugation. So as long as you're not seeing those situations happen, then you're basically good. So in this situation, the biggest loop that you can go through is the one that does include the nitrogen and oxygen. Basically, you're going through the perimeter of the molecule. And what you want to notice right here is that the nitrogen has a lone pair. However, this nitrogen is part of a double bond. So this is an sp2 hybridized carbon. So this lone pair is literally pointing, um, or it's first of all orthogonal, and it's pointing away from the pi system altogether. So it doesn't actually overlap with the pi system at all. Now, on the other hand, the oxygen right here is sp3 hybridized. So one of those lone pairs is going to be orthogonal to the pi system, but the other set of lone pair right here will be totally parallel to the system. So we're going to count two electrons as part of the pi system when we do the full count. So we start by saying, okay, so here's a pi system, so one pi bond. We have another one right there. We're counting this lone pair of electrons from oxygen in the count. We're counting that pi bond there. And additionally, notice that we are going through the two carbons that make up the double bond that goes, basically through the middle. So we're going to basically count that as well, right? And you could also say, well, you could also redraw this thing, look at the resonance structure, right? And then the idea will be still the same, right? You count the three double bonds in the benzene ring here on the left. You count the double bond where the nitrogen is located. You count the electrons of the oxygen. And either way, right, you count all of that, or you do the resonance structure, and then you look at everything here, and you should see that you have a total of 5 pairs of pi electrons, right? And because that's an odd number, that will tell us that this is aromatic. Okay, now to give you a more complex example. Now, this would not be a molecule that would be considered stable by any means. This is, something with positive and negative charge is going to be pretty reactive, even on itself or by itself. But still, if you look at all the carbons in question, or the nitrogens and oxygens in question, they all either have double bonds or they have a lone pair that can complete the conjugation. Or in the case of the carbocation right here, it has an empty p orbital that completes the conjugation. So we can go through that entire periphery. Now, the carbocation happens to be a the carboanion that we have here happens to be part of a carbon that is sp2 hybridized. So much like the nitrogen here that is sp2 hybridized, they both have a lone pair, but it doesn't matter. That lone pair is going to be completely orthogonal to the rest of the pi system. So we do not count either of those two lone pairs in the pi system count. Now, on the other hand, the oxygen that is sp3 hybridized, one of the two lone pairs will make it in the count because it will be able to remain parallel to the pi system. The second one, unfortunately, will be orthogonal, so it's not to be counted. So with that in mind, just remember that the carbocation has no pi electrons there, so it's necessary to continue having full conjugation throughout the entire ring, but it doesn't have pi electrons. So you do the count, right, around the entire perimeter of this molecule, and you see that you have 1, 2, 3, 4, 5, 6, and 7 pairs of pi electrons. And so once again, that will confirm to us that this molecule is in fact aromatic, under the premise, of course, that the molecule remains planar, right? Because to be aromatic, you gotta be planar, you gotta have full conjugation throughout the ring, and you have to hit the 4n+2 count of pi electrons, right? So under the guides and assumption that this is in fact planar, then we would expect it to be aromatic. Okay, so that concludes the investigation of polycyclic compounds that happen to have heteroatoms in them. So in the next video, we're just gonna have a quick review of spectroscopy as it pertains to aromatic compounds, and that will be the end of the lecture. So see you in the next video.